Hello, and welcome to our second installment of Mathematical Foundations in Physics. Let me first identify the basic information that you should know coming out of this lesson today. All that basic information is contained here in this box. And ultimately, the essential question we're answering here in this lesson today is, how do we communicate the precision of a number? Now, these words, precision and uncertainty, are very much related to each other. So whenever we use the word precision, we are talking about how we're quantifying the uncertainty, and the answer to the question of what's the uncertainty has to do with the precision. So the first element I'll just give you an overview about is that in physics, all numbers must include an uncertainty. We have to think about the uncertainty associated with every number. In the previous lesson, we saw that where numbers come from determines how reliable they are, the certainty or uncertainty we have, and some have infinite precision and no uncertainty, and others have uncertainty. And the way we express that uncertainty is with a plus or minus. Now, the most common place that we have seen uncertainty that pretty much everyone's familiar with has to do with election data and polling data. And so in today's day, we have different polling, and we might have in our presidential election, we would find out that the current approval rating, or the people are polling for example, Joe Biden, and let's say that Biden is polling at 52 plus or minus 3%. And if the president is polling at 49 plus or minus 3%, although what we could see then is that Biden is somewhere between 55 and 49%, and that the president is somewhere between 52 and 46%. And so we can see that given the uncertainty in the polls, there is a significant amount of overlap between those two. And so it's difficult to discern who might win the election based on that polling. And when people don't report the uncertainty, it leads to misleading confidence. In fact, it's disingenuous. And so if they were to just report that Biden leads Trump 52 to 49, we can now see when the uncertainty is reported that statement is meaningless without the uncertainty. And so if we take that concept further to apply it to all numbers, however we arrive at them in physics, we want to be thinking whenever we say something like our reaction time is 234 milliseconds, well, plus or minus how much? That's really what we're talking about there. That there are some, similarly, in addition to us having to report uncertainty with every number, there are different concepts of uncertainty. There is absolute uncertainty, there is percent uncertainty, and there are these concepts of the upper and lower limits. What I just outlined for you here is that if we take Biden, we would say it's 52 with the upper limit at 55 and the lower limit at 49. That's all we're expressing there. Where the president is at 49 plus or minus 3 means an upper limit of 52 and a lower limit of 46. And so we want to be thinking about how those upper and lower limits relate to each other. So the first convention for communication that we have, that we want to use, has to do with absolute uncertainty, and that it follows the rules of significant figures for addition. In other words, the same decimal place. The second rule for the convention of and communications is that analog uncertainty is always 1/2 the smallest increment, and that the digital uncertainty is always the smallest increment. It's equal to the smallest increment. We'll see that a little bit there. Now, in terms of the word uncertainty, I'd like you to pause the video for a minute and read over this definition or excerpt of the word uncertainty that I've included for you. And then I will go over the highlights when you return. So uncertainty, what is uncertainty? It involves situations involving imperfect or unknown information, like the polling information, the example I gave you up above. It applies to all kinds of things: predictions of future events, like an election, physical measurements that have already been made, or to the unknown. This uncertainty comes because of things that are partially observed, stochastic environments, and the word stochastic, it basically means random processes, random effects, as well as, and this is important, due to ignorance, indolence, or both. Now, ignorance does not mean stupidity. Ignorance means just simply not knowing. That's what ignorance is. Indolence means laziness or lack of effort. Or it could be both. We just could be ignorant of all the processes involved and we didn't put in enough effort. It occurs in all kinds of situations. It is a fundamental transcending concept of really all human endeavor. Insurance, philosophy, physics, statistics, economics, finance, psychology, sociology, engineering. If you name it, there is something involved where there is uncertainty, even the law. And so uncertainty is a big concept not only in physics, but for all human endeavor. So if you remember from the previous lesson that numbers come from 5 different places, and I won't recount those here. And each one of those, however, has a different level of precision or uncertainty associated with them. Every one of them does. So how do we communicate this precision in a number? Well, when it comes to counts, here we have these Easter eggs. And of course, we can see that there are 1, 2, 3, 4, 5, 6. So the number of Easter eggs we have there is 6. It has infinite precision. It has an infinite number of significant digits. An infinite number of significant digits. There is no uncertainty whatsoever about whether there are 6 eggs there. However, and this is where this becomes tricky and may provide a little bit of discomfort in you when I say that, is that what if someone came along, as would have happened for my 3-year-old daughter, if she were counting these, she might have only counted 4 or only counted 5. It turns out in that case, she is incorrect. She is wrong. She did it incorrectly. So there is no uncertainty associated with this number. Her number is invalid. So we don't attribute uncertainty to something where people did it wrong. And where this comes up oftentimes is many students come up and they use this expression, human error. This may be human error, but we never really use the word human error in real scientific study. Human error is not a word we should ever use in physics or in our laboratory work or so forth. We need to be more specific. In this case, it was done wrong. It was done incorrectly. It's invalid. We don't use it. It's wrong. That is different from when we take a measurement. And we'll come back to that. This isn't a measure. This is counting. So all counts must be done correctly. If it's done incorrectly, it's thrown out. The study's thrown out. The data's thrown out because it's wrong. And we can show that it's wrong. There's nothing open to interpretation as to how many Easter eggs are present in that picture. So let's take a look at the mathematical constants, which we mentioned before. Now, there's a variety of those. So we already went in depth about this ratio 1/2 and that there's no uncertainty. It's exact. There's infinite precision. And similarly, we have a 1/2 here. And when we get to going to that formula in depth, we'll see exactly where that comes from. But it turns out it comes from exactly the same place as this 1/2. So it also has infinite precision. We get to pi. This is a little more different here, but this is a number that is not a whole number. It's not made up on of whole numbers that we easily recognize, although it may be equal to the fraction 22 sevenths. And we have to be careful because if we use 22 sevenths, then we may say it has infinite precision. But if we use 3.14, it has a different level of precision. So if we're doing a formula, say pi r squared, and we use 3 for pi, then it has one significant digit. If we use 3.1, it has two significant digits. In this case, if we use 3.14, it has three, and so on. So if we are choosing to round or truncate a constant that does have a definite value, even though it's not an integer, we would ascribe those number of significant digits to it. So in this particular case here, 3.14159, although pi has infinite significant digits, 3.14159 has 6 significant digits. And so we want to be very careful about where that number comes from. Now let's talk about single measurements. Measurements we make using an analog device. An analog device is a device where humans judge the numbers reported. We have to pass some kind of judgment. And this is what people tend to think of when they think of human error. This is not what scientists call human error. It's what we call random error. In other words, we would expect different persons in isolation from each other to make an estimate of the measurement slightly different from each other. So that error in this case doesn't mean mistake. It does not mean mistake. It just means variability. There's a whole field of statistics, and you could take courses in this, and it's a wonderful, wonderful, gorgeous field of study. I happen to love it very much myself. But the word error really means variability. Error in this case means uncertainty due to one of those three factors we mentioned before, ignorance or indolence, etc. But it really refers to the variability that arises from a complex set of circumstances. In this particular case, if we're measuring the length of something, it's about just the variability in how humans will judge it. Now, as you already learned in chemistry, and some of you were unfortunately reminded with our first laboratory we were investigating lengths, that the length that we would measure here requires that we report a distance. So in this case here, if we're measuring this line, we have 1 centimeter, and it's more than 1, so we have 1.1. And what humans are very good at is identifying the midpoint between two things, between, in this case, 1.1 and 1.2. Now, I might judge that to be just a hair over the halfway mark, which would be 1.15. A hair over that might be 1.16 centimeters. So you'll note in this case that the uncertainty is in the 6. Given that humans can judge 1/2 pretty reasonably, let's take a look at what we might expect from people making a judgment about a measurement. Now, if someone said, in this case, that it was 2, or they said at one point it was 1.2 or 1.1, in that case, if they went beyond that or beyond that direction, we would say they are actually using the ruler incorrectly. It's not reasonable, given the scale of this device and this image here, for someone to choose something that is more than 1/2 this distance. So this distance is 0.1 centimeters, and 1/2 of that distance then is 0.05. So in other words, we do not think that it's reasonable for someone to choose a measurement greater than 1.21 or less than 1.11. So in other words, we're saying it's 1.16 plus or minus 0.05. Now, this is the convention for communication that scientists everywhere agree to use. And this is oftentimes why, and part of the reason why, in chemistry, you didn't learn so much about adding plus or minus on it. Because if a scientist knows this rule, it's given that if you used an analog device, that it should not be more than 1.21, or nor should it be less than 1.11. So that is not only how we make a measurement, it is also how we report that uncertainty. And that certainty is what we would call the reading error. It has to do with the variability due to reading the device. And so it's actually unfortunate and prevents students from understanding that we refer to it as error. But really, it's the reading variability, plus or minus 0.05. If it's beyond that, we think there's something wrong. The person's using the device incorrectly. And so it warrants further investigation. Or does the person actually know how to use the ruler? All right, so let's break this down a little bit more. The starting position of measuring this line was here. And, it's lined up on the ruler, and we might say that is 1.00. Now, if we're lining up that ruler to that line that's in place, let's say it's an object, we're lining that up. We adjusted it, and our eye told us that we judged it to be at 1.00. But we could be wrong. Different persons would line that up differently. So the lining up of that could be plus or minus 0.05. The end position, we said, was 2.16. I said was 2.16. But then again, I could be off by 0.05. So when we subtract these two, we get a 1.16. But if you notice, the right end could be slid one way or the other in terms of its judgment, and so can the left end. So it turns out that when we're lining up both ends of this thing, we add these uncertainties and we get 0.10. Now, this means that our value of 1.16 could be as large as, in truth, 1.26, and as small as 1.06. So because we are judging both ends, the uncertainty in this case is two times the reading error. So not only does the uncertainty depend on the measuring device itself, it depends on how we are using it. If, for example, each one of these things on the ruler had a bump, and this object that we were measuring could slide up to that bump, then we're no longer making judgment at the left end. So we would report an answer of 1.16 plus or minus 0.05, because there wouldn't be any uncertainty here at the starting position. And so there's a great deal of precision and attention to detail that we need to pay in making our measurements. So we have our upper limit, which was the value we got, plus the uncertainty, which was these two added together, minus the uncertainty. That leads us to the concept of absolute uncertainty. So we have a value of 1.26 all the way down to 1.06. And if we take those two, we get 0.20 over 2, and that absolute uncertainty is plus or minus 1.10. So that's the absolute uncertainty. It's 0.10 centimeters. And that's kind of critical, that the absolute uncertainty is plus or minus 0.10 centimeters. The uncertainty itself of 1.16 plus or minus 0.10 are both expressed in centimeters, 1.16 centimeters, 0.1 centimeters. So that's with the absolute uncertainty. We're expressing the uncertainty in absolute terms. The percent uncertainty is that absolute uncertainty divided by the actual measurement, which in this case we said is 1.16 times 100. Or sometimes we just report it as the number without multiplying it by 100. But that's how we get that percent. Now I'll pause for a moment while you figure out what that percentage is. So what I got when I did my mathematics is I got 8.620. And I'm going to report a lot of decimal places, 689%. Now, when we look at our numbers that went into this, so I know where to round this. This had 2 significant digits. This has 3, so my answer would be 2. So ultimately, we would report this as 8.6%. So the other way we could express our uncertainty would be to say 1.16 plus or minus 8.6%. So given our measurement, we were almost 10% uncertainty making that measurement. Now, there's one more detail that I would like to point out here, and that has to do with these numbers. Given the value and the upper limits and lower limits, we can ask ourselves, is there any uncertainty about whether it is 1 centimeter? There's complete agreement about the ones. But if we look at the tenths place, we don't know if it's 1.0, 1.1, 1.2. In fact, if we rounded these, we would have 1.3, 1.2, and 1.1. So we don't have agreement about the tenths place. So the question I would ask you is, what business do we have talking about the hundredths? We don't. If we don't know what tenths place it is, we can't possibly be talking about the hundredths place. So given this uncertainty, which is so large, the final correct answer we would express in this case would be 1.2 plus or minus 0.1 centimeters. Notice it agrees with what we have here. But notice also it is always true that the decimal place of the uncertainty will agree, and the uncertainty will always have only one significant digit. And that should be that should make sense if you think about it, because if it involves 2 different decimal places, then it's introducing uncertainty into 2 places. And if we don't know what's going on in the tenths place, we certainly have no business talking about the hundredths place. So the first rule is to be aware of that these 2 should agree. And secondly, the uncertainty should always and only have 1 significant digit. Now, what does that mean for the percent uncertainty? Well, we could leave it. We could still say it's 1.2 plus or minus 8.6%. Or we could give an overestimate and say 1.2 plus or minus 9%. See, the beauty of keeping this at 1 significant digit here, which it should always be, is that we always want to overestimate. So if it were 8.2%, we would still say 9%, because it is more honest to overstate the uncertainty than it is to understate the uncertainty. Wow, that's a lot of information for you there on analog uncertainty and the different types. So now let's move on to a digital device. Now, what's different about this is that the reading uncertainty is always the smallest increment. So let us imagine now we have this reading over here, and I'll rewrite it, 11.0256 grams. The uncertainty is in this place. The uncertainty is in the 10,000ths place. So this number has 6 significant digits, 6 sig digs. So we have a balance, and we have the ability to zero that balance. So when we zero it, the reading should be 0. And we'll hold off on the plus or minus there for a second. The end mass is 11.0256, plus or minus 0.0001. So the mass then is 11.0256. And the overall uncertainty, the digital scale was set to 0, and so that has 0 uncertainty. So this becomes 0.001. When we've zeroed the balance, this is like using a ruler with a stop, the case where we can push something up against it and we don't have to judge. So in this case, our value is 11.0256. The upper limit is 11.0257, and the lower limit is 11.0255. The upper limit is 11.0257 minus the lower limit, 11.0255, all over 2. And lo and behold, we get a 0.0001 grams. So you'll notice here that the absolute uncertainty is equal to the reading error when you're only having to judge it once. Now the percentage, we can see 0.0001 all over 11.0257 times 100. And you could pause the video here and perform your own calculation. Now, some of you may have already caught this, that I wrote the number down incorrectly. It's not 0257, it's 0256. We're going to see it's going to turn out not to make that much of a difference, because the percent uncertainty is 0.0009069.8%. Now, this only has one significant digit, and of course, we know that we can only report one significant digit. So, in this particular case, we could write the absolute uncertainty, or the number in absolute terms, as 11.0256 plus or minus 0.0001, or we could express it as 11.0256 plus or minus 0.0009%. In other words, in this case, we're talking about negligible uncertainty, negligible error.